Yes, and the topic is quantum and topological photonics, and I will jump right into it. And these are actually two very big fields in photonics, obviously, both quantum photonics and topological photonics separately. We're going to try to tackle them together. So obviously, we will not be able to touch on a lot of the. We're only going to focus on just a few concrete examples, but I think. Uh, we're still gonna see some nice illustrations of how simulations can be used to analyze these systems. And before I jump into Tidy3D simulations, I did want to spend a little bit more time maybe than usual to set up the background for specifically the concepts that will be relevant to the systems that we'll examine later. Now, the quantum part of this presentation and of this webinar is actually pretty simple. We're going to be studying how quantum emitters couple to nanophotonic structures. And quantum emitters are basically can be a lot of different things, but the important thing is that essentially for almost all practical applications of in quantum computing, quantum communication, and so on, we want them to couple strongly to the electromagnetic field because we want to make them either communicate or to control them using light. That's maybe there are some applications where light is not involved, but in most quantum, let's say, computing schemes, whatever your qubits are, you need some light interaction as well. And beyond just strong coupling to the EM field, ideally what we want is strong coupling to a single channel or to some very well controllable channels. So it might not necessarily be a single channel, but we want the light to couple exactly into a channel, a waveguide, a fiber, or anything that we can control, and we know that we're not losing our photon somewhere. And finally, we want ideally to be able to also turn this coupling on and off. That would also be like very beneficial. So tunable, controllable, strong coupling of quantum emitters to light is what this is all about, and what a lot of the nanophotonic design is aiming to do when it comes to the to quantum emitters. Now, the topological photonics part is going to take me a bit longer to talk about some of the important concepts for what we're going to simulate later on. And I did try to, I think if you're completely new to the topic, things will probably not be very clear, but I was hoping that at least I can give the core concepts that people can afterwards, follow up on to understand better. So with that said, yeah, I guess I'll just jump right into it. So topological photonics, by now, it's been more than 15 years. So what I'm actually showing here on the right is the first experimental realization of a photonic topological insulator, and that came out in 2009. So it's been more than 15 years, and it's been a very active field in research and development. And there's so many different systems that qualify as topological photonics. But overall, usually the reason they're called topological is that there is some sort of a topological invariant that can be associated to the system. I'm not going to go into detail about that, but one reason why they have also been very interesting is because often there's an associated edge state, which is essentially a state that exists at the interface between a topological system and a trivial system, for example, air or like a PEC sheet or something like that, which is guided along this edge and also immune with respect to imperfections or obstacles, as is shown here. The light can just go around. So that has been one of the certainly the field is giant, and there's so many different applications and things that people are thinking about, but certainly that has been one of the main drivers historically of topological photonics. So having transport that's robust with respect to disorder. Now, the system that we're first going to look at is a photonic topological insulator that actually is kind of analogous to the quantum spin Hall effect from solid-state physics. And so I wanted to take a step even further back and talk a little bit about the quantum Hall and quantum spin Hall effects as they come from solid-state physics. because basically everything in topological photonics it usually first comes motivated from our solid-state physics colleagues. And this is a review paper on that topic. If you want to learn like really the fundamentals of topological physics, that's a great start. This is where I've taken the images from. But yeah, so very quickly, a quantum Hall insulator is a phase of matter that can happen in some materials when you apply an external magnetic field. And then what happens is that this external magnetic field creates a state at the interface, an edge state again, between this quantum Hall material and an insulator, which can only propagate in one direction. So for example, it can only propagate to the right. Usually it's a single edge state. You can have more, but for simplicity, we can discuss that. Within the band gap of the material, there is just this single state, and there is no possibility for elastic scattering into a backward propagating state. There's simply no backward propagating state. So obviously this has very strong protection against disorder. It does require an external magnetic field, so that's one potential downside, and it can be quite strong. The quantum spin Hall effect was a big discovery in 2005 by actually one of the authors of this review paper. And that is actually intrinsic due to spin-orbit interaction in some materials like graphene, for example. So the big difference is that it does not require any external magnetic field. And that actually is really, really nice. But the difference, essentially, that this, compared to the original quantum Hall idea, here you do have states that go both ways. You have a state that goes right, and you have a state that goes left. But the states are also helical, let's say, and meaning that the direction of propagation is locked to the spin of the electron. So the states that are going right are, let's say, spin up here in this diagram, and the states that are going left are spin down. And the really crucial observation of the original 2005 paper is that these states are still protected against disorder. So states going to the right and spin up actually are not allowed to elastically scatter into the states that are going to the left. Specifically, structural disorder that preserves time reversal symmetry. So non-magnetic disorder, for example, cannot do that. But that turns out to be something that's very specific to electronic systems, and that actually doesn't translate as easily to photonics, as we'll see in a few slides. Now, both of those have, like analogs of both of those systems have been done in various photonic systems. These are some of the early examples. The first thing that I showed in my first slide is the external magnetic field system, which is basically analogous to the quantum Hall effect. The problem here is that this was achieved at RF frequencies and an external magnetic field, and the gyro optic effect was used. So materials that react to external magnetic field, which in photonics, so in optical or near infrared frequencies, this is basically very hard to do. We don't have such nice materials, and to make it in a compact device, especially, it's very unpractical. One of the probably the first system that was kind of analogous to the quantum spin Hall effect was composed of coupled resonators, where the spins are something like the clockwise and the counterclockwise rotating modes inside the ring resonator. And that does have the same signature. Seemingly, it has the same signature as the quantum spin Hall effect, where you have helical edge states, spin up and spin down, going in opposite directions. But fundamentally, it actually turns out to be quite different in terms of topological classification and in terms of protection against disorder. So while the quantum spin Hall effect for electrons has the strong protection against disorder, this system, for example, it has some protection against disorder if you make the resonator slightly smaller or slightly larger, for example. But if you just have inside the resonator microscopic disorder that scatters the light going clockwise and counterclockwise, then you're not protected with respect to that, and that's something that you will inevitably have. So it's a bit of a killer of this effect in a sense. And why is that a problem? Well, one of probably the highest cited review papers on topological photonics that I'm citing here essentially gives the answer to that, and this box 2 is something that I've recommended to people throughout the years to pay attention to, because I think it's important to understand. But essentially, the fundamental difference is the time reversal symmetry and how it acts on electrons and photons, or on half integer spin and integer spin particles. And specifically for electrons, the time reversal operator actually squares to -1. This is a property of spin 1/2 particles, and it's fundamental to the proof that time reversal invariant disorder cannot scatter the helical edge states into each other. And that is not the case for photons. So actually in 2014, when, for example, this paper discussed this, and I remember discussing with people back then, it sounded like quite a strong limitation to photonic quantum spin Hall systems. And so, we were thinking, okay, I guess some sort of time reversal breaking is needed, either an external magnetic field or dynamic modulation is a common way to induce topological phases. But in time reversal invariant systems, this seemed like a problem. Now, there was a breakthrough in 2015, which partially solved that problem, and which basically showed that really like a proper analog to the quantum spin Hall effect can be implemented in dielectric photonic crystals, essentially. Where essentially the author showed that you can devise a operator which is related to the C6 symmetry of the crystal shown here. And so it's a spatial operator, but it has the property that u squared is equals to -1, specifically for some of the modes. So if you isolate your essentially study to the part of the band diagram that is governed by the modes for which this u squared is equal to -1, you basically have created a pseudo time reversal symmetry that squares to -1. And that's associated with a pseudo spin, which now you have this property that the helical edge states of spin going up and down cannot be scattered into each other because of this spatial symmetry. So this is not as strong of protection as the time reversal symmetry thing, but at least it means that as long as the spatial symmetry is preserved, you actually really have a full analog to the quantum spin Hall effect. Now I'm going a bit fast again here for people who are completely new to this, so I apologize, but I just wanted to give like a very quick overview of the most important concepts, which finally brings me to the system that we are going to look into first and simulate. That was published in 2018, a topological quantum interface. So here the authors had, I guess, several innovations. The first one was devising the photonic crystal in a way, so using the idea from this paper, but devising it for something that can work well in a slab. This is a gallium arsenide slab. So here the holes are triangular, as you can see. This is a small modification on the original idea. The other important realization that they had is that, so the pseudo-spin actually in these systems, it kind of looks like, if you look specifically at the modes of pseudo-spin up and pseudo-spin down that are that are formed at the interfaces between of such topological insulators, they basically look like left and right circularly polarized light. Or if you look at the electric field at the center of this cell here, it looks like something like EX plus IEY for pseudo-spin up, and then the opposite for pseudo-spin down. And so the realization here is that you can actually, if you put a quantum dot here in the center, you can actually use external magnetic fields to control the light to which the quantum dot emission couples to. And so you can make since the helical edge states propagate one way for the left circularly polarized and the other way for the right circularly polarized light, you can make the emitter emit one way or the other controllably. So this is great. This is definitely very useful. And obviously also the same system has the advantage that the channel, once it emits into one of these states, you can guide it around, for example, sharp bends without much backscattering. Now, again, like I said, this is all still subject to the spatial symmetry of the C6 symmetry of the elementary cells, but it does seem to work quite nicely to guide light around. So this is actually the end of my introduction. Maybe I'll take a few questions while switching to the notebook where we're going to simulate that system. Trying to see.
Montre, there is a question in Q&A. Can you see that? So you can...
Yes, I was trying to find it. Now I found it finally.
Great.
Surface state with carrier mobility. This question seems to be pushing my understanding of solid state physics. So I am not sure. I'm not sure I can answer that actually without maybe a bit more of a clarification of the question or without me thinking about it. So if that's the only question, I guess I will leave that one and then, yeah. Yeah, so, okay, there is another question about how strict is the requirement for spatial symmetry. And I would say there have been subsequent papers that study various quantum spin Hall photonic systems that have come to a varying degree of agreement about whether the symmetry breaking completely breaks, the practical usage of these materials or not. I think like surface roughness, essentially, the microscopic imperfections are going to affect the states. There is the nice thing that you can route light without having to worry about how to devise this bend, for example. That's certainly nice. But when it comes to the microscopic imperfections, there are some works that show that at least in some of those systems, like the backscattering in the end is not better than what you would do if you just have a regular, let's say, photonic crystal waveguide at the same group index. I would say the jury is still out about the practicality of the protection. Yeah, so I'm looking at a few more questions here. The bends are restricted to the shape of the unit cell, and that's true. Yeah, like so, but this is just one example of this idea. So in principle, there are other systems. There's also quantum valley Hall effect. There's different topological photonic crystals, but yes, in this example, the bends can only be around these 60-degree directions of the elementaries of the underlying lattice. And then someone asks me to explain protecting against some disorder a little bit more. So that's essentially what I already mentioned as well. If you have disorder that preserves the C6 symmetry of this elementary cell. So if all of the pillars for example, are slightly larger, then that disorder will not scatter your right going light into your left going light. But if each pillar has some microscopic change that's different and that breaks the symmetry, then that is going to be problematic. And that is not the case for the solid state physics, so the quantum spin Hall effect for electrons, in which it really is magnetic disorder or some time reversal breaking disorder is needed to scatter the states. So sometimes, by the way, when people talk about quantum spin Hall insulators, they would call microscopic structural disorder, they would call it like magnetic or like pseudomagnetic because it couples the pseudo-spins. Yeah, but you can kind of think of it like that. You have, now, if you look at the microscopic states, I actually have this is the paper by the same authors that preceded the science paper. It has a bit more information about this particular structure. If you look at the modes, it's hard to visualize them. So this is actually, okay, I guess if we look. So, okay, here, this shows the degree of left and right circular polarization of the two different modes. And they don't look exactly like left and right circular rotating modes. They're more like, you don't really have this in this elementary cell, but you can still think of it, or I still think of the pseudo-spin a little bit in that way. And you can think of it like if you have something like something that rotates one way and something that rotates another, if you have microscopic disorder along this path, then it's gonna scatter. And if you have something that is, let's say, a uniform thing that preserves the symmetry, then it's not gonna scatter. Okay, there's probably more questions, but I guess I'm gonna continue for now with the presentation so that we don't take too much time, and then we're gonna spend time in the end as well answering more questions, and also my colleagues are gonna answer live. So we have recently introduced an example in our documentation, and actually it's very, very fresh. In fact, if you go to our documentation, you need to go to the
Hello, Mantra, sorry to interrupt you. Are you going to share your screen? Because we cannot see your monitor now.
Oh, really? Was I talking
Yes.
without
No. Yeah, I thought it was on purpose because you give
Oh, I was actually showing
introduction.
something. I see.
I see.
Did I stop sharing? Okay, let me see.
I can see the topological edge states example.
Yeah, could you see the presentation? So do you see this?
Yes.
Oh,
Okay.
Okay, great. Looks like oh, I see. Yeah, it was switched on the other monitor on my side. I'm so sorry. Yes,
Okay.
yes,
No
everything's
problem.
good. Sorry.
No problem. Okay. Yeah, so this example I was saying is very new, and the way we currently do our deployment, it's actually not in our latest documentation. It's only in our pre-release documentation. So it's because it was just merged. It will get into latest as well. But if you wanna do this yourself, so you can always go to docs.flexcompute.com. You can download this as a Python notebook, or you can just examine it here, but just note that you need to select the pre-release version to see this topological edge state example that we have just added. I can also just open the notebook that I have opened here. And now I'm just going to go through a little bit of how do you go about simulating this in Tidy3D, giving some tips on how to build this system. I'm not gonna go through every line of code, obviously, but I'm just gonna illustrate conceptually what the code does, or I'm gonna explain what the code does a little bit. So for the global simulation parameters, we just use whatever is defined in the paper, including the structural parameters of the photonic crystal, lattice constant, slab thickness, edge length of the triangles. And then we're going to simulate a system with 20 unit cells in X direction and 16 unit cells in the Y direction. Here we just make a helper function that is going to make a single unit cell centered at a particular location, X0, Y0, with particular parameters for the edge length, for the distance. Oh, I think what I didn't really specify here is that the difference between the top and the bottom regions is simply how far away the triangles are from the center. So on the top, they're a little bit farther out than they are on the bottom. And that creates these two distinct materials which have different topological properties, essentially, which when you make an interface between those two, you get these helical edge states. So yeah, so in our example, we make this function that allows us to offset the triangles by this value r. And yeah, I'm not going to go through the code. This is just what the function does, but we can also visualize the output, and it just makes this one single unit cell composed of 6 triangles. Now, the next thing we're going to do is we're going to make a function that generates a triangular lattice. So this is a unit cell composed of 6 triangles, and then the photonic crystal itself is composed of a triangular lattice with this unit cell, essentially. So at each side of the lattice, there are 6 triangles. So the triangular lattice here, we're just generating a list of XY coordinates of the centers of the sides of this lattice. So if we visualize this, this is what it looks like. And we've already assigned half of the sides to be a bottom half and the bottom and another half of the sides to be the top half. But these are just, here we're just plotting with points the positions at which elementary cells will be located. And now coupling those two functions together, we can, sorry, I don't know why my computer is kind of skipping around. Yeah, coupling those two functions together, we can now set R to 0.94 for the lower half and iterate over the sites that are in the bottom sides list of locations, and then create a unit cell at that particular site location with that R value that corresponds to the bottom photonic crystal. Then we can do the same for the top. These are, again, the values are taken from the paper. Iterate over the sites that are in the top part of the crystal, and at every site make a unit cell that at that site that has that value for R. And by the way, our geometry operations support things like adding. So you can add two geometries together, and under the hood, this is handled by Tidy3D to just create a union of the geometries. So if we just plot now and zoom in, we see that we've created exactly what we've been trying to. This is the one unit cell of the bottom crystal, and here is one unit cell of the top crystal, and we've created exactly the interface. And now we want to place a, we want to emulate a quantum dot by, here we're going to do a point dipole. So in the very beginning, there was a question about, or not a question, but someone mentioned quantum emitters in FDTD. And I should say that we are still going to be emulating here a quantum dot with point dipoles, because this is, for many applications, this is actually perfectly fine. Like if you want to compute the Purcell effect or the the coupling efficiency to the waveguide mode, or even the just the magnitude of the light matter interaction at that position, like using a point dipole is definitely fine. In some cases, you might want to have an actual quantum emitter in FDTD. This is a separate topic. So a nonlinear systems, or so a 2-level system or a 3-level system, or modeling the exact physics. That's a separate topic that we're not covering here. And we might have a nonlinear seminar in a few months where we might talk about some of those things. But yeah, so we're going to model the quantum dot emission here by placing a point dipole. And specifically, actually, to model the helical nature of this system, we're going to place 2 point dipoles to model, in this case, right circularly polarized emission. So, sorry, I don't know why this keeps skipping. First, for the slab medium, we're going to use our inbuilt gallium arsenide model from our material library. The holes are just air. So that's it for the geometry creation. And then for the source, we're going to place a dipole, 2 dipoles, like I said, at one of the unit cell centers at the interface, where the 2 dipoles have orthogonal polarization, EX and EY, and correspondingly a pi/2 phase shift in the time signal of the source. So that's how you can create right circularly polarized light, for example. We're also going to place some monitors. One is going to be just an in-plane field monitor to see what happens. And the other is going to be two monitors of the flux on the left side and on the right side. And actually, okay, I also have a plot of this system in the GUI opened here. So the emitter is somewhere here, actually. I'm not sure why the sources are not showing, but I guess it's because they're buried inside the slab. But so we're going to be monitoring the flux to the right and the flux to the left, and we expect obviously that we should see flux to the right and no flux to the left. I think this is also visible. Yeah, so here you can see where the source is placed, the two sources. And that's it, actually. I guess I should mention as a practical advice when simulating photonic crystals that sometimes PML could not be the best choice for the boundaries in this direction, because PML in principle assume that the system is translationally invariant inside the PML. And specifically when you have, like we will have here, when you have a waveguide mode going into the absorber, it's probably smarter to use, for example, we provide an adiabatic absorber as an optional boundary condition, and that's usually a good idea for these systems using something like this. So this is what we do here. I'm not going to rerun the simulation, but I can show you here that, as usual, Tidy3D manages these large 3D simulations very fast. This took 40 seconds. And we see the result that we were aiming for, which is which was predicted by the paper. We can reproduce that result. The emission going to the entirely to the right. Here it's absorbed by the absorber. And if we compare the flux in the flux monitors, so this is the ratio of the flux going to the right to the flux going to the left, we see a strong suppression of the, or like that the flux is basically going entirely to the right. And this happens in this 0.9 to 0.96 approximately micron range, which is exactly where also the paper's prediction of these of the band gap of these crystals lies. So this is all we have presented here. Of course, one could go further and reproduce, for example, this type of going around bands, or also what I have tried is that if I switch the if I switch the phase of the time signal of the two dipoles, so if I do it, if I do essentially a EX minus IEY type of thing instead of plus IEY, then the emission completely reverses and all of it will go to the left. Okay, so I think I can again take a few questions here before quickly going to one more example. Let me see. Yes, 3D, someone commented that 3D simulations just need 40 seconds. Yes, Tidy3D is very, very fast. Can we simulate also strong coupling if we use, for example, a photonic material like TMDs? So I think that's there's levels of how much of the physics of these systems you want to incorporate, but our so Tidy3D actually does support 2D materials. So the TMD can be modeled as a 2D material. And I believe we have some examples of that in our documentation that I think maybe my colleagues can point you to. Yeah, so someone is asking about this point that I made about the choice between PML or adiabatic absorber in a photonic crystal. So the first question is, what exactly makes the PML non-ideal choice for the setup you have? So the PML is defined, but analytically, it is defined for translationally invariant media. So basically that means that you have two options when you truncate your system at this boundary here. You have two options. One is to stop making holes, just have the slab, and then have the PML over it, and then the PML, the analytic formulation works because it's in a translational invariant system. But that means that you've introduced an artificial truncation of your photonic crystal, which can cause reflections, for example. So that's not great. Or the other option that you have is to continue with the photonic crystal inside, but then the analytic properties of the PML do not hold anymore. So you can introduce reflections, or you can even introduce divergence, because PML are absorptive for propagating waves, but they are actually gainy. They can introduce artificial gain for evanescent waves. And when you have structural interfaces inside the PML, these structural interfaces can introduce evanescent waves. And so your simulation, for example, can blow up. So there's multiple things that can go wrong. If you have strong light like this propagating mode inside the PML with materials that are not translationally invariant. The absorber, the price to pay is the second part of that question. The price to pay is basically that the reflection might be higher compared to PML in homogeneous media. And that can be controlled by increasing the number of layers that you have. And then, yeah, the price to pay essentially is that the simulations become a bit more expensive and slower because you might, so for PML, for example, you would just use 12 layers by default, while for absorber here, we use 60 layers. So that makes the simulation a bit larger, but overall, it's in some systems like this, it's the better choice typically. Someone asks to what extent, if any, can be concluded from the simulation that this is a topological state. So we cannot conclude from this simulation this is a topological state. We cannot conclude even if we were to replicate this transition around, or this transmission around sharp bands. Even that is not an actual proof that we have anything topological. We are really replicating an existing study, but if you wanted to really examine whether a system is topological, for example, and compute the invariant and so on, then you would have to, the usual approach is to compute the band structure of the regular crystal, like was done here, and to use the eigenmodes to compute the invariance, for example, a churn number, which, it's the standard way that these things are defined. So you actually need to compute the topological invariant. It's a bit involved. I'm not going to explain more than that, but I am going to mention that this can totally be done, and maybe we should actually prepare an example about that as well, because with Tidy3D, because we can compute the band structure of photonic crystals, and we can also compute the eigenmodes associated with the various modes. And so one can then just plug in the definition of Berry phase and churn number and so on to compute the topological invariance. Okay, maybe I'll... Can we simulate those? Yeah, okay, so there was a question exactly about this. I think I will then move on with one last example. Now, this one is actually, it's with respect to what we've talked about so far, it's only going to be related to quantum emitters again. So there's nothing, technically, there's nothing topological here in terms of topological insulator or photonic topological insulator, but stretching the taxonomy, or not the term topology is used in several different domains. And in the domain of inverse design, which is something that we are building at Tidy3D quite extensively, and we're quite proud of our inverse design capabilities. Topology optimization, so again, nothing to do with topological insulators, but topology optimization refers to usually basically using the adjunct variable method and the usual kind of inverse design techniques to compute gradients of given objective function with respect to the permittivity of some material everywhere or like within some design region, and then using this to optimize freeform optimization, doing a freeform optimization, so creating these kind of crazy shapes that optimize some objective function essentially by using like the whole distribution as a degree of freedom. So you have thousands of degrees of freedom here, for example. This is often referred to as topology optimization, and we also support it in our GUI, by the way. But yeah, again, so I wanted to show this, and again, to make sure that I'm not claiming that there's anything topological here, but it is related to the same concepts that we've been discussing about quantum emitters and enhancing the emission and also enhancing the useful light emission. So enhancing emission into a specific well-defined channel. So what this notebook does is, and this is not the new notebook, so for this, you don't need to be on this version. But what this does is inverse design optimization of the coupling efficiency of, again, emitter that we model as a point dipole. So, for example, a quantum dot inside inside an integrated photonic device, with the goal to have all of the emission be coupled to this output waveguide. So the coupling efficiency, by definition, is the ratio of the power that's coupled to this output channel to the total emission power that's emitted by this quantum dot. Since we're kind of coming towards the end of the hour, I'm gonna go relatively fast through that, but I wanted to kind of showcase this as well, because I think inverse design is also something that many people are interested in, and I think Tidy3D allows you to do it really well. So the optimization, let me see. The optimization is basically set up to, I'm just gonna skip to the illustration of the structure. Let's see if I can explain this a little bit. Yeah, so this is our starting setup. So we have the emitter. We have our design region, which is currently at the beginning of the process. It's initialized as just intermediate permittivity. We have the output waveguide, which we're aiming for. And then we have, as monitors, we have a mode monitor, which is just recording the power that's coming out in the fundamental mode of this waveguide. And then we have a flux monitor that's all around the device, which monitors the total flux, the total power emitted by the emitter. So then by doing the ratio between this power and this power, we get the coupling efficiency. Now, our inverse design plugin essentially allows you to do optimization basically without doing anything special. You just define your simulation in the same way that you would do as if you were doing just a simulation, not an optimization. But then you can compute not just the objective function, so the okay. Yeah, so you can compute both the value of some function that depends on the simulation data and the gradient of that function. So that the flexibility of Tidy3D essentially is that it's super easy to take a simulation and turn it into an optimization. So one could even imagine doing this for the previous example that we investigated. You can start here and then derive some objective function that's based on the simulation data that's returned by the simulation. And you can actually start an optimization without modifying anything of the code above. Here, the objective function is going to be a composite of the coupling efficiency, so the ratio of the model power and the total dipole power, and some penalties that basically come from trying to force the final result to be fabricable. So we want the final result to look well binarized, so not to have any intermediate values of the permittivity, and to have smooth shapes. And for both of those, we provide built-in penalty functions. And we have quite a lot of examples on the inverse design optimization. So I'm not going to go into detail on this, but essentially the objective function combines the two things of both getting what we want and also getting it in a fabricable device. This is the starting coupling efficiency of the device. So it's quite poor. As you can see, like not a lot of the light is emitted into the channel. Coupling efficiency over the spectrum that we're interested in is below 0.2. And long story short, after the optimization, so this figure plots both the fabrication penalty in blue, which decreases as the optimization progresses, and the coupling efficiency in black, which increases as the optimization progresses. And this is the final device, and this is the emission. And it's interesting that essentially what you get, you do get these free-form shapes, but it kind of, there is something that also makes intuitive sense almost. It does seem like the optimization creates something like a small resonator around the emitter, and then also creates this kind of almost like DBR-looking shapes around here to create a mirror that can guide all the light inside this waveguide. And here specifically, we only optimized for the coupling efficiency, and that is very high. It's 97% or something, I think. Actually, here it says 80%, but I think maybe for some reason this text was not updated because it seems like the coupling efficiency is actually extremely high. And the Purcell factor, which was not part of the objective function, so we also got some Purcell enhancement, is only up to a factor of 5 or so because it was not part of our objective function, but in principle one could, the minimum and maximum coupling efficiency are from 97 to 98%. But it's equally easy to compose a objective function that, for example, aims to optimize the Purcell factor or a combination of the Purcell factor and the coupling efficiency. Okay, I think that's all I wanted to show for this, and we are running out of time on the hour. I could stay longer to answer questions, but for now I will conclude with the main part of this. And let me show this final slide is what Ching asked me to leave during the Q&A session, so that also you guys know how you can reach us, and also that we have an office hour that you can book with one of our experts.